An open loop transfer function of the system is given as g of s is equal to k into s square divided by 1 plus 0.2s into 1 plus 0.02s. This is the open loop transfer function of the system. For this system, determine the gain k for a gain crossover frequency as 5 radian per second. This is the question using Bode plot. So if these type of questions are given, the first thing you have to do is we have to sketch the Bode plot of the given open loop system. So in order to sketch the Bode plot, we don't know the value of k. So initially we have to substitute k is equal to 1. Assume that k is equal to 1. For these type of systems, for these type of problems, in order to draw the Bode plot, assume that k is equal to 1 and rewrite the open loop transfer function. Here also h of s, we can take h of s as unity. Then we can rewrite the open loop transfer function g of s is equal to 1 into s square, that is s square divided by 1 plus 0.2s into 1 plus 0.02s. When we substitute s is equal to j omega, here you can see that this is the form 1 plus st format only. So we can directly substitute s is equal to j omega. Then g of j omega is equal to j omega whole square divided by 1 plus 0.2 j omega into 1 plus 0.02 j omega. Now we can write the magnitude and phase angle of the given transfer function. What is the magnitude of the given transfer function? We can write the magnitude, that is modulus of g of j omega, as modulus of g of j omega, which is equal to omega square divided by 1 plus 0.2 square root of 1 plus 0.2 omega square into square root of 1 plus 0.02 omega square. This is the magnitude equation, and the phase angle equation will be the phase angle of g of j omega is equal to, what is the phase angle? Here you can see that there is an s square term or a double differential in the numerator. There is an s square term in the numerator, or there is a double differential in the numerator. A square term, that is indicates there are two open loop zeros at the origin. The s square term in the numerator indicates that there are two open loop zeros at the origin. So we know that when there is an s term in the numerator, the phase angle will be plus 90. Here there are s square term in the numerator. Since there is an s square term in the numerator, the phase angle will be, the numerator phase angle will be 2 into plus 90, or it will be plus 180 degree. It will be plus 180 degree. because of this s square term in the numerator, the phase angle will be plus 180 degree corresponding to the numerator. If it is an s cube term in the numerator, it will be plus 90 into 3, that will be plus 270 degree. Now we can complete the equation of phase angle, that is plus 180 degree. Now we can see that there are two first order terms in the denominator. So corresponding to the first order term 1 plus 0.2 j omega, the phase angle will be minus tan inverse 0.2 omega, again minus tan inverse 0.02 omega. This is the equation for phase angle. Now here we can see that there are two zeros at the origin, that is corresponding to s square. So here there are two open loop zeros. So the maximum phase angle contributed by the two zeros will be plus 180, and two poles at the two poles that represents by two first order terms, 1 plus 0.2s and 1 plus 0.02s. So the maximum phase angle contributed by two poles will be minus 180. So the total phase angle will be plus 180 minus plus 180 plus minus 180, that will be 0. That means since there are two poles and two zeros, at higher frequencies the phase diagram will be converging to 0. Since there are two zeros and two poles, the phase angle contributed by two zeros are plus 180. Phase angle contributed by two poles, maximum phase angle contributed by two poles will be minus 180, and the total phase angle will be 0 degree. That means at higher frequencies the maximum phase angle will be, or at higher frequencies the phase angle will be going to a constant at 0, approximately 0, that you can see. Now we can write the table, we can find out the corner frequencies. The next step is to find out the corner frequencies. So corresponding to corner frequencies, omega c1 is equal to 1 divided by 0.2, that will be equal to 5 radian per second. Now omega c2 is equal to 1 divided by 0.02, that is equal to 50 radian per second. So what is the next step? If we find out omega c1 and omega c2, the next step is to form the table. Okay. Next steps is to form the table. So we can form a table omega g of j omega. So the next step is to form the table corresponding to omega, and we have to find out for different values of omega we have to find out the magnitude and phase angle. Also we have to find out the magnitude in decibels. So since we have 5 radian per second, I am taking the lowest frequency or omega L as 0.1 itself. Now 0.1 and I'm taking the next frequency as 0.5, 1, the next corner frequency 5, 10, 50, that is the next corner frequency, 100, 200. So corresponding to this, the magnitude values are respectively 0.01, these are the values of different values of omega, and for these values I have find out the magnitude in decibels, and phase angle in degrees. So here you can see that the phase angles are starting from plus values and it is actually decreasing. When the frequency is 1000, omega is 1000, the angle in degrees is plus 3 radian per second, and if you check the value or if you find out the value for 10,000 or 10 raised to 4, the angle will be 0.3, only it will be 0.3 degree. So if you find the phase angle in higher frequencies, it will be nearer to 0 value only. Now we can mark the scales in the semi-log sheet. So the first thing I am marking from, since we have taken the value of omega from 0.1, I am marking the first value as 0.1. Okay, so here you can see that corresponding to the 1 I have marked 0.1. Now here this is the second one. Okay, corresponding to this one you can mark corresponding to this one I can mark 1, corresponding to the next one, that is here, I can mark 10, here it will be 100, and here it is 10 raised to 3 or 1000. Now also we have to mark the corner frequencies. So what are the corner frequencies? What are the frequencies we have chosen? 0.1, after that 0.5. So 0.5 will be where? 0.5 will be in between 0.1 to 1. In between this decade or in this band, 0.5 will be there, and we can mark the 0.5 here corresponding to the marking 5. So in between that band we have to check the marking 5. So here you can see that the marking 5. So corresponding to this point we can mark the angle, corresponding to that point we can mark the frequency 0.5. So this is 0.5, and our next frequency is 1 that we have already marked, and the next frequency is 5 radian per second. So 5 radian per second will be in between this band 1 to 10. So in between this band you have to check the marking 5 in the upper side, and in the lower side corresponding to draw a straight line corresponding to that straight vertical line we can mark the frequency 5 radian per second. Now also we can mark 50, that will be in between 10 to 5. So this will be in between 10 to 5, that is 50. Next we can mark 200. For marking 200 will be in between this band, that is 100 and 1000. In that we have to check the marking. In that band we have to check the marking 2. So you can see the marking 2 here corresponding to this vertical straight line. We can mark 200, frequency 200. So it will be approximately here 200. Now we have to mark the gain in decibels. So we can see here it is starting from minus 40 dB and it is going to plus 47.7. So we have to take the frequency band accordingly. in the last two problems we have obtained the gain in decibels as plus to minus, but here you can see that the gain is actually in the first value, that is corresponding to 0.1, the gain is minus 40, and corresponding to 1000 the gain is plus 50 degree. So you know we can mark the gain corresponding to the given values here in the y-axis. So when you mark here, our maximum value should be in this point. So unlike the problem that we have discussed earlier, in those type of problems we have obtained highest gain corresponding to lower frequencies. Approximately we have obtained plus 40 dB or plus 35 dB corresponding to the lower frequencies, but here you can see that at lower frequency the gain is minus 40, and at higher frequency the gain is plus 47. So we have to mark the gain starting from, in the upper point we have to mark the plus dB gain, and it should be start from downwards, it will start decreasing. So here I am marking plus 40 corresponding to this point, plus 40 dB, because always the gain should start from higher value, the above value should be higher. Here it will be plus 60, now plus 20, 0, minus 20, this is corresponding to minus 40. So we can check that in all the problems you should mark the gain in decibels. In the upper part it should be maximum value, and it should start maximum to minimum value. It should go like this, the scale should be drawn like this. So now we can mark the points corresponding to all these values in the graph. Corresponding to 0.1, we have already got corresponding to 0.1. What is the value corresponding to 0.1? Corresponding to 0.1, the value is 40 dB. So this is our first point. Corresponding to 0.5, the value is minus 12. This is 0.5, and this will be corresponding to minus 12. Corresponding to 1, the value is 0.1. 0.1 means it's approximately 0. Now corresponding to 5, its value is plus 25. Corresponding to 5, value is plus 25. Corresponding to 50, it is corresponding to 10, it is 32. And when frequency is 50, the value is 45 decibels. So it will be approximately here. Corresponding to 100, the value is 47. It is also approximately here. And corresponding to 200 also, the value there is no much change in the value. So we have got the magnitude plot here. So now we can draw all these points, join all these points in a smooth curve, join all these points. Okay, so this is our magnitude plot. When k is equal to 1, this is our magnitude plot. The next step is we can plot the phase angle. So if you plotting the phase angle, then also if you choose the scale, it should start from higher degree to lower degree. So here the higher degree is corresponding to plus 178 and lower degree corresponding to plus 3. So our scale, we can select the scale from plus 180 to 0. So I am marking 0 here. This is 40 degree. This is 80 degree. $120 degree. $160 degree. This is plus 200 degree. So this will be corresponding to plus 180 degree. Now we can mark the phase angle. So corresponding to point 1, the phase angle is plus 180. So here you can see that the two plots will mix. Okay, because there are the range of values of two phase plot and magnitude plot are different. There is a chance that there will be some crossing of two plots. So corresponding to point 1, the value is what is the value corresponding to point 1? That is approximately 178. So that value we can mark here corresponding to point 1. Corresponding to point 5, the value is 173. So it is here. And corresponding to 1, the value is 167. Corresponding to 5, the value is 129. 129 means it will be somewhere here. 120. And corresponding to 10, the value is 100, 105. Sorry, corresponding to 10, the value is 105. Corresponding to 50 omega, or omega, when omega equal to 50, the value in degree is 50 degree only. So 50 degree means it will be somewhere here. And when omega is 100, the value is 29. And 200, the value is 15. And when it comes to 1000, it is actually coming down to 0. So we can draw the phase angle plot now. I will start from here, this point. So we know that phase angle plot is independent of the gain k, because gain k means the angle of gain k is 0. So when we change the gain of a system, there will not be any change in the phase angle, and phase angle will remain constant, or phase angle plot will remain constant when changing the value of the system gain. Appo gain, when you change the gain, then phase angle will not change, only there will be change in the magnitude and magnitude plot of the corresponding system. So we have obtained the magnitude plot and phase angle plot of the given system. Now the next step is, we have to find out the gain k when the gain crossover frequency is 5 radian per second. So what is gain crossover frequency? Gain crossover frequency is the frequency at which the magnitude of open loop transfer function is unity or 0 dB. So here the magnitude plot crosses the 0 dB line here, that is corresponding to this frequency. So we can see that corresponding to, actually when gain k is equal to 1, when we have plotted the magnitude plot when k is equal to 1, the magnitude plot crosses the 0 dB line at omega is 1 radian per second. But we have to find out the gain crossover frequency where omega gc equal to 5 radian per second. So the first step is we have to find out what is the value of gain when omega gc or omega is equal to 5 radian per second. So from the graph you can see that this is the point, right? This is the point where omega is 5 radian per second. This is the point where omega is 5 radian per second, and corresponding to this point the gain is plus 25, right? Corresponding to this point, the gain is plus 25 dB. So in order to change the gain crossover frequency to 5 radian per second, what is gain crossover frequency? At gain crossover frequency, the gain should be 0 dB, but now the gain is plus 25 dB. So we can write it here. When k is equal to 1, we have plotted the magnitude plot. At that time, when k is equal to 1, when you find out the gain for omega is equal to 5, the gain when the frequency omega is 5 is plus 25 dB, that is we have obtained this from the graph. Now what we have to do is we have to make (5 radian per second as gain crossover frequency or omega gc. We have to make 5 radian per second as omega gc. So that means in order to make 5 radian per second as omega gc, means at omega gc, that is at 5 radian per second, at 5 radian per second the gain should be 0 dB. At 5 radian per second the gain should be 0 dB. So what you have to do, you have to redraw the plot. In each of these points, you have each of these points. In each of these points, you have to redraw by changing the magnitude plot. When omega GC is 5 radian per second, your gain should be 0 dB. So I am redrawing the plot. So corresponding to this value, that is omega GC is 5 radian per second, gain should be 0 dB. That means here, okay, corresponding to omega GC, that is 5 radian per second, the gain should be 0 dB. Now in each of these points, I have subtracted minus 25 dB from this point, right? Because this point is plus 25 dB, so I have subtracted minus 25. I have subtracted 25 dB from this point. So this point minus 25, I will get 0 dB. Corresponding to each of these points, I have to subtract a plus 25 dB. So when I subtract from plus 40, when I subtract from plus 40, what will it be? It will be, here it is minus 20, and the lowest point will be corresponding to minus 40. Sorry. Here it is minus 60, and this point will be corresponding to minus 80. So when I subtract 25, when I subtract plus 25 dB here, it will be minus 40 minus 25 will be minus 65. So it will be approximately here. This is minus 65. I have subtracted plus 25 from this point. From this point also I have to subtract plus 25. It is minus 12 plus 25. Minus 12 minus 25 will be minus 37. It will be approximately here. From each of this point you have to subtract a 25 dB. At 10, the value decibels is 33, approximately 33. 33 minus 25 is 8 decibels. So when we redraw the point corresponding to, to when omega GC is 5 radian per second, our graph will be like this. So this is the graph when magnitude plot when omega GC is 5 radian per second, because we can see that corresponding to the point corresponding to 5 radian per second, the gain is 0 dB now. right? So corresponding to 5 radian per second, the gain is 0 dB. So now we have plotted when omega gc as 5 radian per second. Now what is the next step? We have to find out the gain k. We have to find out the gain k for the given system. So we already know what is the equation for gain k. We know 20 log gain k. So we have the equation for magnitude of g of j omega that I have written here. In order to find out the value of gain k, 20 log of k into omega square divided by square root of 1 plus 0.2 omega square into square root of 1 plus 0.02 omega square. Okay, 0.2 omega square, that is equal to, from the graph we have obtained, that is equal to minus 65 dB, because in the initial part only I have considered. So in the initial part we can see that this is minus 65. When you subtract plus 25 from this minus 40, it will be minus 65. So I can write the equation as 20 log into k into this part, that is the magnitude of g of j omega, that is equal to minus 65. Okay, so I can rewrite this equation as 20 log k minus 20 log of omega square divided by 1 plus 0.2 omega square into 1 plus 0.02 omega square which is equal to minus 65 dB. So what is minus 65 dB? Minus 65 dB is the decibel at omega is equal to 0.1, right? Because from the graph we can see that at 0.1 omega the magnitude in decibel is minus 65 for the new magnitude plot at which omega gc is equal to 5 radian per second. When omega gc is 5 radian per second for the new magnitude plot, when omega is 0.1, you can see that at this point corresponding to omega 0.1 the magnitude is minus 65. So this part, that is corresponding to this part, when omega is equal to 0.1, the gain in decibels that we have already obtained in the table. What is that? When omega is 0.1, the gain in decibel is actually that is minus 40 dB. So we can write that 20 log k minus the gain in decibels that we have already obtained when k equal to 1, or when you substitute for omega equal to 0.1 in this equation, when you find the gain it will be minus 40 dB. So 20 log k minus 40 dB equal to minus 65. Sorry, there is a change. This is plus, This sign is actually plus because we have the equation k into omega square divided by, we have the equation k into omega square divided by square root of 1 plus 0.2 omega into square root of 1 plus 0.02 omega. So the equation is actually k into, when two products are coming, log of two products, log of A and B, A into B will be log A plus log B. Since it will be, hence it will be 20 log K plus the magnitude of this term, that is minus 40. So we can write 20 log K equal to minus 60 plus 40, that is minus 25 dB, and log K is minus 25 by 20, and what is the value of K? In order to find K value, you have to find anti-log of minus 25 by 20. It will be 0.05. The value of K will be 0.05. When value of K is 0.05, you will get omega GC as 5 radian per second. Thank you.